Let's say you take a moon, a nice solid gravity-bound chunk of rock, and you slowly start bringing it closer and closer to a planet. What happens? Well, at first, nothing dramatic. It just orbits peacefully. But keep going, bring it too close. And suddenly, that moon starts to come apart. Not because of collisions or impacts, but because of gravity itself. And the exact point where this breakup starts? That's what we call the Roche Limit. It's basically the line in space where the gravity from the planet overwhelms the self-gravity of the moon. Outside that line, moons can survive. Inside it, they're done. They get torn to pieces by tidal forces, and those pieces can end up forming rings. This one idea, first described by a guy named Edouard Roche in the 1800s, explains why Saturn has its iconic rings, and why Earth doesn't. So here's the deal. Gravity pulls everything together. That's why stars are round. That's why planets are round. Moons? Round too. But when you've got a planet and a moon, things get more complicated. That's where tidal forces come in. Tidal forces happen when gravity pulls on one side of an object more than the other. Think about Earth and our moon. The side of Earth closest to the moon feels a stronger pull than the far side. That difference creates tides. That's what causes ocean bulges. Now take that idea into space. A planet pulls harder on the near side of a moon than the far side. If the moon is far enough away, no big deal. But if it's too close, those forces can literally stretch the moon apart. That's the Roche limit. Cross it, and you're toast. Let's take Saturn. It has the most spectacular rings in the solar system. But why rings instead of more moons? Because those icy ring particles, every one of them, are orbiting inside Saturn's Roche limit. They can't clump together into a new moon. Gravity won't let them. The tidal forces keep pulling them apart before they have the chance to stick. Saturn isn't alone, by the way. Jupiter, Uranus, Neptune, they all have rings too. They're just harder to see. But the same rule applies. The material in those rings exists inside each planet's Roche limit. Now flip the question. Why doesn't Earth have rings? Well, it could have. Billions of years ago, something the size of Mars slammed into Earth. That collision threw massive amounts of debris into orbit. Some of that material was far enough away to escape Earth's tidal grip. It clumped together and became our moon. But if that debris had stayed closer, within the Roche limit, it wouldn't have formed a moon. It would have broken into pieces and created rings instead. Beautiful? Sure, but temporary. Rings don't last forever. Even Saturn's aren't permanent. Over time, all that ring material slowly spirals into the planet due to orbital instability, micrometeorite impacts, and drag from the planet's atmosphere. Cassini data suggests Saturn's rings might only be 100 million years old, and they might vanish in another 100 million. Let's bring this back down to a concrete example. Phobos, one of Mars's moons. Phobos is slowly spiraling in toward Mars. Eventually, it's going to cross Mars's Roche limit. When it does, tidal forces will start ripping it apart. Piece by piece, it'll become a ring. And that's not hypothetical. It's going to happen in about 30 to 50 million years. So yes, rings can form from moons. And yes, they can disappear too. Technically speaking, the Roche limit depends on a few key things: the mass of the planet, the size and density of the moon, and whether the moon is rigid or fluid. A rigid object, like a solid rock, can resist some deformation. A fluid object, like something squishier, starts to stretch early. That means it breaks apart sooner. So the Roche limit is larger for fluid objects than for solid ones. That's why there are two versions of the Roche limit: the rigid and the fluid version. One assumes the moon holds its shape. The other assumes it starts to deform before it breaks. But even the rigid model makes one big assumption: that the moon is basically just a pile of rocks held together by gravity. Not always true. Artificial satellites, for instance, are held together by engineering, not gravity. That's why the International Space Station doesn't break apart, even though it's way inside Earth's Roche limit. What about Earth now? Could we ever get rings? Not naturally, no. There's no large moon close enough to break up, and no asteroid or comet is likely to wander into a perfect orbit and stay there long enough to form a stable ring. And even if one did, Earth's atmosphere would probably drag the material down, or the moon's gravity would disrupt it. But if Earth had rings, it would be wild. You'd see glowing arcs in the sky, maybe visible even during the day. But the downsides would be real too. No dark night skies. Satellite navigation and space travel? Way harder. Some areas of the planet would experience longer winters due to the rings casting shadows. It would be beautiful, but it would also mess everything up. Here's the short version. Too far out, you get a moon. Too close in, the moon's toast, and you get rings instead. Tidal forces decide what survives and what gets shredded. If you enjoyed this video, consider dropping a comment and don't forget to subscribe.